Like the storage. No, not the storage.
No, we're talking about number systems. Tera's a group of engineer notation, but in binary, it depends on power of the two, right? So a kilo in binary is 1024. And then a meg would be 1024 K. And then a gig would be 1024 meg. And then a tera would be 1024 gig, right? Does that make sense? Yes, no? What don't make sense about it?
Like how is it, is it double?
Well, it's going up a power, so it goes in tens. So on powers of twos, in regular engineering notation, you go in powers of tens, but you go 10 to the third, 10 to the sixth, 10 to the, right? You understand that? To the ninth. In binary, we go on powers of twos, and it moves in tens instead of threes. So the smallest binary equivalent of engineer notation would be 2 to the 10. Then it don't double every time, right? It's just like if I was talking about decimal, I'd say, okay, what's 1,000? Well, what's 100? What if I was going in powers of tens? You'd say, okay, we go from 1 to 10, which is 10 to the first, and then we'd go 10 to the second, which would be 100. Then you'd go, which would be 1,000, right? You understand? But binary works with powers of 2 instead of powers of 10, right? You understand that? That makes sense now? So like a K, so we have 100. Well, what's a K? Well, it's a what? And then what's a meg? It's a 1,000 thousands, right? You understand that? Understand? So we keep moving like that once we get up to K, right? You understand that? So here we move in powers of 2. So this is the way it actually goes right here. But you could also do it this way, right? So here we have 1,024 to the first, and then the second, the third, the fourth, the fifth. If you said 2 to the 50th, that would be exactly the same as saying 1,024 to the fifth. Come up and give you exactly the same answer. But what the problem we have, it's just like when I write a number up here. Why do we see that? What automatically we see that number as a base 10 number, right? You don't understand that? So if I come up here and write, I might have got 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, got 1 too many. Right? Let's do it. 1, let's see. Of course, this would be 1, 2, 4, 8, 16, 32. If it's binary, 64, 128, 256, 512, and this would be 1,024, which is the same as 2 to the 10. But what we want to do is we want to see it as what? This is what we want to see it as. Right? Understand that? So normally when people say a gig of memory, they think it's a what? A gig, a million, right? But it's not. It's this. when we're talking about computers, we're dealing with the base 2 numbering system. We're not dealing with a base 10 numbering system. And even manufacturers and people get so confused with that. And this is why if you ever look at the capacity of a hard drive, if you've got a 2 gig drive, you go up there, you're expecting to have 2 gigabytes worth of storage, and you look in there, it's usually less because of the amount of space that's eat up by just keeping up where stuff is. So anytime you store anything on a USB drive, USB uses what we call a file allocation table. If you ever look at your hard drives use what they call a new technology, NTS, new technology, FS file system. In fact, though, what we do is we eat up a bunch of information here and here. We usually refer to this as a header. And then this right here would be referred to as the trailer. Well, when they come up and say you got a 5 gigabyte drive or 32 gigabyte thumb drive, if you ever look at the capacity, that's 32 gigabytes, including the header and the trailer. So the header says, I belong here, this is what I am, I belong to this file, and the trailer is where we keep up with error checking the information. And then in the center, this would be the data. So when I send information over the internet, we send it in, they call these packets. But most people say when you say you got a terabyte or a gigabyte, your mind is in base 10. But when we talk about this, it's binary, and all these storage devices are in really base 2, right? Does that make sense? We can send data, information. We're not talking about power. Right now, we can't send power over the air, right? We can send information over the air, but we can send information 2 different ways. We can send it in parallel, or we can send it in what we refer to as serial. So parallel means every bit we're trying to send. So if I'm going to send 8 bits of information, if I sent that parallel, it usually would require 16 wires. Why is that? It requires 16 wires. Why 16? To send 8 bits. Over wires. That's a good point, but no, it's not send receive. Okay, this would be like me having a light bulb out here, and I run 1 wire to the light bulb. This light bulb won't come up. Okay, so every device is going to require 2 wires, right? You understand? So 16 bits of information usually takes 16 wires, because what they do is they put a return for every data wire, because it reduces the noise. Okay, 16 wires for 8 bits of data. But if you go back and look at some of your old parallel interfaces, I'll go see if I can find the cable. You'll see there's a ton of wires on there. 16 data, you got a ton of wires, because for every data signal wire, you got a common, right? You understand that? Does that make sense? So, but the other way we can send it is we can send it serial. Now, what do you think serial means? Huh? Not one direction. Well, not one wire. If I'm going to send it on wire, I can never use 1 wire. Why is that? Well, you can't say a positive and a common. We always have to have a return, right? You understand? Because if I always had a positive and a common, I couldn't send data, or we couldn't send data, because most of the stuff. So AC, when I send AC, there is no such thing as a minus and a plus. Why is that? Because it's constantly changing direction. Alabama Power is running at 60 cycles a second. That means that sucker, that thing changes direction every 8.3 milliseconds. So the minus and the plus are doing what? Changing. Most of our data communication is basically AC, especially over cable. It gives us the ability to do what we call modulated. So there's really no plus and minus, but we've always got to have what? 2 wires. I mean, if I came over here and put a light bulb, and then I hook this up to AC, so this is a symbol of an AC, I still got to have a what? Another wire. But there's no minus and there's no plus because it's only there for 8.33 milliseconds, right? You understand? And that's for 60 cycles a second. That's 60 cycles a second. You know, these carriers we're using now, they're up at AM. You can, on your radio, it sends it out as an AC signal, even though it's going through the air, and we're up in the gigahertz. Good gracious, gigahertz, it's going to change directions all the time, right? You understand? But we've always got to have 2 wires. So the minimum number of conductors I could send serial over would be what? 2. And then I might be a transmitter and receiver. We'll talk about that. This could be what we call a transceiver. What would a transceiver be? It's a device that can not only do what? Transmit, it could always do what? Receive. We'd have the same thing over this way. But what we'd end up with is we'd end up with 2 wires. Well, it depends. In computers, it would be 16 wires. Because what happens is we're trying to run 2 wires side by side. And what happens is anytime I try to put a current into this one and they're right next to each other, it would induce a voltage into the next one if it was a signal wire, if we try to use one ground or one column. But if I use a ground between each signal wire, then this can't induce a voltage through ground, right? Does that make sense? So normally in computers, if we're sending the information parallel, we do it 2 wires per bit.
Okay, so about 1 5.
In series, we're dealing with 2 wires. Got to have at least 2, right? You understand? So what would be the advantage of parallel over serial? Huh? Oh yeah, it's a lot faster. And the analogy we use is like going to Birmingham up there on a single lane road. Sending 1 million cars to Birmingham. 160,000 cars go through downtown Birmingham every day. 160,000 cars on the 2-lane road.
So we say that serial is the roadway and parallel is the interstate.
Sort, yeah.
Okay.
So you know, the more lanes you have, the faster you can move through, right, on a parallel road. It doesn't mean I can still get it there in series. It just take a while, long time. Like what is it? Fairway Boulevard up there.
Yeah.
That's where they're dumping everybody off up there to get around the closure. So serial is cheaper, and then sometimes we have no option but to use serial. Like I'm trying to send stuff to my cell phone. Is that parallel or serial? It's got to be serial. I only got 1 air, right? You understand? I don't have 18 airs out here. I can send that individual airs. I can send that information through. So sometimes serial is the only way we can do it. So broadcast information and what's coming to my cell phone, wireless Wi-Fi, of course, it's serial anyway. So the advantage of parallel is that it can always be faster. The advantage of serial is it's going to be a lot cheaper. Now, a lot of times we use serial because the equipment we're sending the information to don't need parallel. Does that make sense? The F4 Phantom, it had 2 big old Pratt & Whitney turbojet engines in there, and the jets could fly, the engines could fly the plane faster than the airframe could handle.
Oh my God.
So the F4 never was able to run those engines wide open. So that was a waste of a lot of
time and money.
Money, yeah, but that's if they went below this size, they wouldn't get the speed they wanted, right? Does that make sense? So that would be like me putting a jet engine in a Volkswagen, right? Couldn't handle, so what we're saying is some devices don't need parallel. Like me up here on my keyboard. Do I need parallel up here for my keyboard? No. I ain't no way in the world I could type up in the gigahertz. So the keyboard is a serial interface. It's a serial interface. This is serial. We call it BGA. It's a serial interface. Of course, we're going to some parallel. It's called DDI interface because of the number of bits we're trying to transmit now on these extremely high resolution. But your TV is serial. It comes through. How many cables do you have coming into your cable box? From the cable company.
Oh, just one.
Just one. Right. That's what I meant. But if it was parallel, every channel will have their own cable. So, you know, we got over 100 channels. That means there'd be 100 cables coming in. Well, even trying to get them on the pole, right? Understand? So these are serial. We don't use well, that's not true. Allen Browning PLCs still use a form of COM, call it a data highway. It uses a COM port. But USB, this is serial. In fact, the S in USB stands for serial, universal serial.
You said universal.
Huh?
You said universal. Universal serial.
That's what it stands for, universal serial. That's what USB stands for. And it's serial.
Serial base?
Bus.
Bus.
A bus is a term we use in electricity where we have a common wire and then we come up here and we can connect different things to it. You know. This is serial ATA. This is our predominant method for mass storage devices now. And it's ATA is Advanced Technology Attachment. That's Y, not U. This is the primary. Used to we had ATA. Serial ATA came out, and the other one became known as parallel ATA. Now the problem with the hard drives is even mass storage devices. USB is technically a slow interface. But the devices that we hook it up to are not fast devices. Does that make sense? I think we got another version of serial ATA coming out. I think 4 is out right now. But this is the one most often put out there. This gets us all the way up to 5 gigabits per second. But it's downwardly compatible. So if you have a USB 3.0 interface and you put a device in there that supports a 1, it's going to be able to connect to it and communicate okay. It's just like our networks, our Ethernet networks are downwardly compatible, which takes us. The serial ATA, this is the primary method now to run high-speed mass storage devices like disk drives, stuff like that. So here's, we have 2 ways we can send data. We can send what we call serial. We can do what we call synchronous serial, which means the receiver would only read the data on an edge of a clock. So if it was time to this edge right here, we call it the rising edge, then what would be the data I would be sending? Well, I'd come up here to my data. This would be a 1. This would be a 0. This would be a 0. This would be a 1. This would be a 1. This would be a 0. And this would be a 1. And so what happens on serial, on synchronous serial, the receiver only looks what's on the input when it's being timed by clock. But this required 3 wires. We had one for our common, we had one for our clock, and then we had another for data. So this would be like me, everybody's covering their eyes up here, and I'm writing words up here on the board. And then every time, if you just sit there and open them, right, you understand, I might not be through with a word, but every time you got your eyes covered up, every time I got a word up on the board, I'd go beep, and what would you do? You'd open them up, and then you'd close them back, right, you understand? And that way I'd be able to transfer a sentence to you. If you did it randomly, then what would happen is you would open your eyes, right? You understand? So we got to have some method of timing this. This is called synchronous serial. So synchronous in digital means it's timed with a clock. A clock. That makes sense? And we have synchronous parallel. Inside your computer, it's all synchronized. So normally inside your computer and also inside your cell phone, the data is processed in parallel, and it's synchronous parallel. So that means we sacrifice at least one conductor to time everything. And when you start looking at computers, that's the one thing you're looking at is how fast is it timed it, right? But then we have asynchronous serial. Asynchronous serial, what we get back here is we send it at a precise rate. So what happens if this guy right here is going at 100 megabits per second, and this guy here is going to receive at a what? 100 megabits per second. All we do is send a sequence. What they do is inside the header, so we send data in packets. Well, inside the header, what they do is they run a sequence of 10, 10, 10. And then what that does is that gets the clock on the receiver and synchronized with the clock on, right? So that would be like me up here writing data, but I'm writing it at a precise rate. I'm writing words at a precise rate. And then before I start, I say now. And then you would have a mental clock in your head, and I'm writing them at 1 word per second, and you open your eyes every second. Does that make sense? And in that way, we would be in sync. But what I've done is I've saved the conductor. This is the primary way we send that. USB uses asynchronous. This is an asynchronous. Serial ATA is asynchronous. And what this does is it saves wire. Because you got to have stuff inside the packet anyway, so why not just sacrifice a few bits to get the receiver in sync with the transmitter? Does this make sense? So USB is it's an asynchronous serial bus. But you got all these devices out there, so you got to have a header in there. So you say, okay, you got to have an address in there saying, okay, this is device. How many devices can you hook up to a single USB port? It's like 256 devices you can put up to a host port. So every time you plug one in, it's got a little memory in there that transmits and it say, this is who I am. And then your computer assigns it an address. And it says, okay, I'm at this address. And now, once we got an address, all the packets go out and it says, I'm addressing Brian. We got 2 Brians here. Brian Calhoun, right? You understand? And nobody else even listens because it's not their what? It's not their address. It's just like these cell phones. These cell phones, when they transmit that packet, they transmit your number in there, right? You understand? And all the other phones, they're receiving. So you receive every call that comes to me. Right, you understand? And I receive every call that comes to you. But what happens is that when it reads that header, it says, okay, this is for this address, and then your phone just does what? just ignores it because it says it's not for me. Plus, it's encrypted, thank goodness. It is, but you know, the government, our government knows how to encrypt that stuff, so they can receive anybody they want to. But it's what we call 128-bit encryption. So that's 2 to the 128th possible of encoder codes that it can send to your phone when it establishes communication. So that's a lot of numbers they have to go through, yeah. So the encryption we use it for. Used to it was straight up. It was just straight up audio they sent. And you could get a police scanner and play around with it, and you could tune in people's cell phones. That's before it was encrypted. Now what's happened is that this gives us a problem because I'm trying to send information over distance. And I don't have it over here, guys, but we got it over in motor controls. I don't know if I can rig something up over here. But anytime we send current through a conductor, it sets up a magnetic field around it. We're not going to worry about the direction. We have a line. And so what we have is we have the ability pauses. I'll bring them. So to induce a voltage into a conductor, what we have to have is, number one, we got to have a magnetic field. And 2, we've got to have a conductor. And 3 is we got to have what we refer to as relative motion. Which means we got to either got to cut the conductor through the magnetic field, or we got to move the magnet across the conductor. And this is going to induce a voltage into that conductor. Now it's going to be really small. It might be a microvolt. So we wouldn't even be able to measure this for a meter. But what we do is we come over here and we loop the wire. So that means when the magnetic field cuts 2 of them, then instead of getting a microvolt, we get what? 2 microvolts, because it would be like doing this. And we refer to this as series 80. That makes sense? So we got to have a bunch of loops of wire. So just like I do on my electromagnet, I have a bunch of loops of wire because the magnetic field being produced in one doesn't generate enough of magnetic field to pick up anything, right? You understand that? Does that make sense? So what determines the amount is the strength of the field. And number 2 is the number of conductor loops. And number 3 is the speed of the motion. Speed of the motion. Number of loops. This is the number, electromotive force. Which is some people call it EMF. This is what we refer to as voltage. So you'll see a lot of formulas, instead of using V for voltage, they use E. You see it all the time. Because what's so funny, you say V is equal to I times R, and you say V is equal to 30V. So you got V on both sides of the equation, right? Which don't make sense. Mathematicians say that. So you'll see some books that teach E is equal to I times R. So then they'll say E is equal to 30 volts, and now you don't have V on both sides of the equation, right? Mathematicians don't like to say V is equal to V, right? That mathematically, that don't make sense. So you'll see a lot of books teach E, and E stands for electromotive force. We call it EMF. To create an electromotive force, we can do it different ways. We can do it magnetically, which is the predominant way of doing it. This is what Alabama Power does. They do it magnetically. This is what your car does. That generator you have out there, and most people call it an alternator, is doing it magnetically. It's spinning a magnet and cutting across coils of wire, which produces a voltage, right? You understand? Now, what it's doing, but it's spinning an electromagnet, because what happens is when you're driving your car, what's constantly changing? The speed of the motion, which means you get up to 70 miles an hour, it'd burn everything up in your car. You're sitting at a red light and nothing would work, right? You understand? Unless we had a way to regulate that. So what they do is they have a sensor out there, we call it a voltage regulator. And what they constantly doing is doing what? They're changing the strength. And that's one advantage electromagnet has over a permanent magnet, is we can control the strength of the magnetic field. So as your car slows down, the output of your alternator tries to go down. Your regulator increases the strength of the field. And it keeps your voltage out of your alternator a little over 14 volts. We say we have a 12 volt system, but it's not. It's basically 14 volts, but it'll run on 12 volts. Because anytime your car is running. So that's the way, right off the bat, you can tell if your alternator's working. You can go out and get a voltmeter. If you have to jump your car off, jump it off. Look across your battery. If it's measuring 14 volts, it means your alternator's fine. But your battery won't charge. So what would that mean? That usually means you got a loose connection or you got a bad battery, right? If that makes sense. So you can tell in a heartbeat. That's basically what it does when you go to AutoZone and they just clamp that thing on there and they say, well, your battery's dead, right? They'll jump your car off, right? You understand, and then basically measure the output. But we run up with a problem in that if what do I have right here? Well, anytime I have a voltage, I have current. And what I'm doing is I'm constantly changing the magnetic field. So what happens, if I got another serial wire next to this is going to try to induce a voltage into that wire. We call it crosstalk. If you're in communication, you talk about, and you actually pick it up sometimes. You know, you pick up multiple. You ever picked up your phone? Not much on cell phones now because it's encrypted and got that code on there. But on the old days, you could pick up a regular phone and you could hear people in the background. It was crosstalk, and all it was is there was no, all it did was ran wires beside each other. And I don't know if y'all have ever seen those things bundled up. So the problem we have, and this is why on parallel they put a ground for every conductor, in that it's hard to induce a voltage to the ground. But what would happen is if a magnetic field would fly through this one, it might induce a voltage and change that to a 1, and it wouldn't do anything to that 0 right there. I mean, to the 0 to your ground reference. So they had to come up with this is why serial and parallel used to be limited to so small lengths. You know, now we can run a network cable of 100 meters, which is 330 feet, but it's not using this garbage right here. It's using another technique. So the technique they understood, and this with electronics came on, we came out with a special amplifier called a differential amplifier. So what happens is we never use 0. We don't use a common. What we do is we transmit the signal, two of them 180 degrees out of phase. So the opposite of each other. So this would be my signal, And notice what the other one is, it's exactly opposite. So we always have a difference of potential. Since we have a difference of potential, that means we can send current, right? Does that make sense? But we don't use common. Now what they did is we came up with an amplifier referred to as a differential amplifier. And what it does is it only allows signals that are moving in opposite direction to go through. So what it would do is these are moving in opposite directions. And then of course what's going to get through is the true data. So this would come over here. Now what happens, we have a magnetic line of force comes through here. These guys are, we use what we call twisted pair cable, which means that your two wires are twisted together. And then what happens is if you do a signal into this one, you're going to induce the same signal into that one. Well, the problem is that this is no longer differential. We call this common mode. So what the differential amplifier does, it rejects common mode signals and only lets differential signals pass through. So what differential signaling then did, it basically eliminated electromagnetic interference. And now we can run these cables a long way, and we can run them at extremely high speeds, even though it would never be in parallel. So differential parallel would run a lot faster than differential serial, right? You understand that? But differential serial is fast enough to keep up with the hardware that we're trying to run these interfaces on. That makes sense? For differential serial ATA, that's up to, I don't know, I need to go, did I put them there? Yeah, so serial ATA, this is differential signal. This is up to 6 gigabits per second, and that's the last version, guys. I don't know, I need to go back and research and see if we got any more versions. 6 gigabits per second, the fastest we can, think about how fast can you send a plastic platter on a DVD drive? You ever watch Mythbusters? When they slung in things apart? Metal drives, metal platters that we spin on our hard drives, the fastest they want to spin those things is 7,200 RPMs, which to us seems pretty fast, but this rate is still fast enough to keep up with a hard drive spinning at that speed. So if I don't have the hardware that will keep up with parallel, then why use parallel? Does that make sense? So just about all our interfaces are going to, most of our external interfaces where we connect the external devices on the computer are serial. This is serial. Of course, this don't need to be fast, right? How fast can I move the mouse, right? Are we okay? That makes sense? So most of our interfaces now are Ethernet. Wired Ethernet is differential serial. Are we okay? Any questions? Parallel, separate conductor for each bit, expensive, very fast. We still use it inside the computer. So inside your cell phone, inside the processor and everything, it's still parallel. It's when we go out and start communicating with the outside world where the predominant connection is. Are we okay? So this is parallel. This is only using one return, which is very noisy. So that's, like I said, most computer interfaces that use parallel uses 2 wires per. And we don't hardly, you don't hardly see parallel. We don't hardly see parallel anymore. Because when I connect to a computer, I'm connecting through what? Serial, yeah. Even HDMI is serial. It's just extremely high speed, but it uses differential instead of this guy right here. This guy uses ground. So this is still fairly slow, right? Resolutions on this, I think we got up to 1024 by 768 pixels on this guy. That was the fastest this guy would run. And now they're talking about, what, 4K? Yeah. That's definitely HDMI. But it uses differential and it don't use a common. Switches and electronics make and break connections. angle switches, electromagnetic relays, semiconductor devices, which are used inside what we're doing. Digital logic has been around for a long time. Originally, it was implemented using relays. Are we okay? Any questions here? Relays. And I got some relays, but they're really small. But the way a relay works is we have a device we call a solenoid. And what we do is there's a tube through a solenoid. Now I got one of those. So this is a solenoid. So what we got is the same thing that I've got here, but I've got a tube in the center. And then this plunger or armature can move in and out pretty easy. And you can see what happens to a solenoid. Now, so what we do is when we put that magnetic field on there, what does it do? Well, it pulls that armature into the tube in the center, right? Does that make sense? And of course, when I turn it off. Now, if I had a spring on this thing, so a solenoid only generates force in one direction. So that means to get it to return to the other direction, I've either got to use gravity or I use a spring. Make sense? Where do y'all run into these things at? Huh?
You got some, is that the same though?
Yeah, it's just a solenoid switch. Well, the one on your door, the ones on your door is a little motor because a solenoid can't be used on the locks on your door because you would be able to lock them, but you wouldn't be able to unlock them, right? So it's got a little motor in it. But dishwashers use them, washing machines use them to turn the hot water on and cold water off. Ice makers use them. People that have the ability to electronically lock and unlock doors. So that's pretty popular now where you can go in and do it with solenoids, right? Does that make sense?
Because I thought it untransmitted one door. So how can they do that?
You can unlock doors, but I don't think you can lock them with it, but buzz you in, right? And so,
oh, okay.
Yeah, so a spring could bring it back. So you could leave this thing here out like this, right? Understand? And then when you hit the button again, the spring could do what? Push it back. Now, I'm almost sure electronic door locks for houses, I'm almost sure it's solenoid. Because we want them in a very small space, right? So what probably happens on that is, I don't know which way it goes. I don't know if it keeps it energized, keep it locked, and then when you hit the button, it would turn it off and the spring would bring it back. I'm not really sure. But if I was to take this and put a switch out here, so when this come up here and hit that switch, so I had a spring on my switch, or I mechanically, and then when the solenoid went back, the switch would open, and the solenoid went this way, the switch would close. Then that's what we have. That's a relay. That's all a relay is. It's just a solenoid. But what it does is it opens and closes switches. So instead of now me having to get up there and flip a switch, we can do it electrically, right? Understand? So that's what a relay is. And like I said, we got little tiny relays. So what we can do is we can come up here and what we do when we draw these things, we use a method. One method that we used to draw on is something called ladder diagrams, which means if this was DC, well, this would be my two power lines, whether it's AC or DC. And then I could come over here and put a contact right there. And the coil that controls the relay, we draw that as a circle. Then what we do is we give these relays names. So right now I'm going to call it, let's call this CR1 and call this CR2. And then the contacts or the switches that's controlled by that, we draw it like this. And what do you think that's a symbol for?
Relay.
Yeah, this is a light, but it don't have a line. And let's say I assign this contact to CR1 and I assign this contact to CR2. So what happens when I close this switch, this contact will close, but the light still wouldn't come on, right? Does that make sense? So what I would have to do is I would have to come up here and close this one and that one, and then the light will come on. That makes sense? Well, this is a type of logic we refer to as what type of logic? And. Now we could keep coming and we could put multiple contacts in here. So I just did 2, and 2 is just easy to explain. But you got to understand, I could have done what? I could have come up here and put another one and call this CR3, and then put another contact down here. Now CR1, CR1, and CR2, and CR3 would have to be closed. So for like, well, this is digital, guys, because the switches are either what, open and closed, and these contacts are open. Now, if I come over here and did this, and this is CR1, CR2, CR3. When would that light turn on? If CR1 was on, or 2, or 3. So this is type of logic that we call OR. So, and all your guys have to be true, right? You understand, before the output is true. On an OR, any has to be true. So this is logic, guys. But this is logic done with relays. So relay logic has been around a long time, as long as relays. Relays were the first method that we used to electronically or electrically control a system. And so what happens when we turn it over to electricity is we can control electricity, right? You understand? So relays are what originally brought in what we call automated manufacturing, where I come up here and I press a button and now everything comes into play. But it used to be done with relays. Now we do it with computers, or we do it with integrated circuits. This is electrically, so these guys, this is called a ladder diagram. Can you see how I got that name? Because it looks like a ladder. And each one of these individual little circuits, we refer to these as rungs. So these are relays. These are small relays. We got them all different sizes. We got them in integrated circuits. You can actually see the cylinders there. And we put power. This is where we connect the coil. We call that the coil. That's what's represented by the circle symbol. And then when I come over and hit that, it pulls this flap down, and what does it do is contact. It makes them a break. We can have some little tiny relays too, which we can. Now the disadvantage of relays, and I know it's not great, the disadvantage of relays takes several milliseconds of current, several milliamps of current to operate. It's slower because it takes, you have to energize the solenoid. Solenoid's got to generate a magnetic field. It's got to pull that plunger down, right? You understand? So real solenoids are not extremely fast, or relays are not extremely fast. Are we okay? This makes sense? But we can do logic with these. We just can't do extremely fast logic. So this computer right here is running up in the gigahertz. I got to do ands and I got to do ors. I can't do it with relays. I never do that. We have some of our PLCs that have relay outputs. So this is an Added Valley PLC. It has relay outputs. Now, what's nice about relay outputs is it don't care if we can put AC, we can put DC, we can put and the voltage level you put out there. So they're more versatile as far as what we can put on them, but we can't run any extremely high-speed devices with this thing because of the time it takes for the relays to respond, right? We call it reflexes. You know, our reflexes can only move so fast. Well, the problem, and that's not the output. See the output right here. But each one of these would be a contact, but it says volts AC, volts DC if I can get my camera. So what I do is I decide what's nice about relay contacts is they don't care if you put AC across. So this light switch over here would run off 100, it would switch 120 volts DC, just like it would switch 120 volts AC, right? You understand? The contacts don't care what you put, what type of voltage you put on it. They don't care what type of current you put on it. All it cares is how much voltage you put across them, right? You understand that? So what's nice about having relays on a PLC is that I can run AC devices on one device. I can run DC devices on the one next to it because we're controlling contacts. But the problem is that we've got some pulse width modulation. I could not run a DC drive off this using pulse width modulation because we're going to run that around 50 kilohertz, and I cannot switch a relay at 50 kilohertz. So even though this PLC supports pulse width modulation, I can't use it on this one unless I run real slow devices, right? Does that make sense? So relays are great. They do logic. What's nice about relays is I can use DC to control AC. So the coil might be a DC coil, but my contacts are controlling AC, right? You understand? My DC coil might be running on 26 volts, but I might be controlling 6,000 volts up here on my contacts. But the big problem we have with relays is they're not what? Fast. They're not fast. We can't use them in high-speed applications that requires extremely high speed. But we can do logic with relays, no doubt about it. I mean, and this is what they're trying to do. I think they're trying to show a little bit of delay. So what we do is, let's go ahead and take a break, guys. 2 minutes. One of the first semiconductor devices that they came out with was something referred to as a diode. And a diode is made from semiconductor material. Now, a diode works like plumbing, and in fluid it would be what we call a check valve. A check valve is a valve that only lets fluid flow in one direction. Well, a diode only lets electrical current flow in one direction. So we have two parts of the diode, and this is the electronic symbol, by the way. We have an arrowhead. It's supposed to be filled in. A lot of people don't do that. And we have a bar on one side. Then we got two leads coming in. The arrowhead itself, we refer to that as the anode. The bar is referred to as the cathode. Bias, bias is a DC voltage. Now this is in electronics applied to a semiconductor. Control its characteristics or conduction characteristics. So when a diode is forward biased, it conducts. When it's reverse biased, it don't. To forward bias it, we have to make the cathode more negative than the anode, or less positive. And it's not a perfect switch, so when we, generically speaking, we say when it's forward biased, it acts like a closed switch. When it's reverse biased, it acts like an open switch. But it's not a switch. It will always drop a voltage when it's forward biased. We predominantly use a semiconductor made out of silicon, and the silicon drops around 0.7 volts when it's forward biased. And it drops the entire voltage when it's reverse biased. So follow me so far. This is the guy that converts AC and DC. You run into these all over. So we have an alternator on your car, but your car is a DC system. So that means they've got they call them rectifier banks. They're rectifiers, and they're nothing but a bunch of diodes that only lets that AC run in one direction, which would give us DC, right? You understand? Now there's a little more to it. You got to add some more stuff to filter it out. But these guys only let current go from AC to DC. Their main function in life is to convert AC to DC. So Alabama Power, my TV runs off of DC, but yet I plug it in the wall. So there's a rectifier assembly inside there that does what for us? Converts the AC over to DC. And all it is just a bunch of diodes, and then some other components too to smooth it out. But we can also do logic with these things. These guys were first used in a type of logic. That's its main function in life. In logic, most of the time we can do logic with AC, but predominantly, what advantage does DC have over AC? That's not an advantage. No, power's equal V times I. Well, V could be AC, I could be AC current, so you can't say it. The advantage of DC over AC. Why do we have DC? Why do we have AC? I mean, what advantage? DC can be electronically controlled. AC is almost impossible to control electronically. So all your electronic devices run off of DC because we can precisely control it. We can do exactly what we want to with it very easily because we're not trying to control something that's constantly changing direction. Now, what we use AC for, AC creates induction. It automatically creates induction. It's got everything it needs to create induction. If I put current through an AC conductor, it generates a magnetic field, right? You understand? And then plus, it's got motion because it's constantly doing what? Changing direction. So it has current, it has motion, so it can induce voltage. So that means I can come over here and I can bring two coils, a bunch of coils together. I can couple that with a big chunk of metal, and I can put more turns out here. And so what that means, I might be putting 120 volts AC right there, and I might be getting 560 volts AC over there. So what we can do, since this thing generates a change in magnetic field, and I put two coils real close together, I got everything I need. I got one coil generating a magnetic field. It's cutting the other coil, and I can change the loops on this side and that side. So I can step AC up and I can step AC down. Real easy. Well, the problem is Alabama, Alabama Power. They're not trying to sell you voltage. They're not trying to sell you current. They're trying to sell you power. Power is work, right? You understand? So if I know power is equal to V times I, then I know I would be equal to P over V. So it means the higher I can make that voltage, the less current it's going to require to send you that power. Every wire has a resistance. If I tried to send 1,000, this is the problem you have on your car batteries. Your car batteries require 50, 60 amps to turn that dang thing over, and that's probably in the summertime, probably almost 100 amps to get your car turned over in the wintertime. If your conductor had 1 ohm of resistance in it, your car would never start. You cannot, because if you try to pull 50 amps through 1 ohm, it would drop 50 volts. So that's why your battery connection down to that starter are what? They're big old wires, right? And they're very short because it has. So if every conductor has a resistance, and we're getting power at this college from up in Tennessee. We're on TVA here, guys. Vesper's on TVA. They're not on Alabama Power. So where does our power come from? Well, it comes from TVA. Well, how can they get the power to run this college down to this college? They send it at an extremely high what? Voltage. Requires little current. I is equal what? V is equal to I times R. So now my current gets down low. So if I transmitted power at 750,000 volts, I could send 750,000 watts of power with 1 amp of current. But what's the problem with high voltage? The higher voltage is more dangerous, right? And the higher voltage is looking for earth ground. So these big power transmission lines, where are they? Well, they're way up in the air, right? You understand? And they're spread far apart, right? Y'all understand that? So the closer I get to earth ground, what am I going to have to start doing? I'm going to have to start stepping that voltage down. Because two things, I'm getting closer to earth ground, and another thing, I'm getting closer to me. Right? You understand? So what we can do is we can step that volt AC up for transmission, and we can step it down for safety. So even though there might be 2,300 volts up there on your power pole, when it gets your house, you're getting 240 and 120, right? Understand? Now devices are designed to run off a certain voltage. So you can take a light bulb that's designed to run on 120 and put it on 240 because it would try to produce 4 times the power. And you can't run something that was designed for 240 around 120 because it would do 1/4 the power. So power varies with the square of the voltage. Y'all understand that, right? Yes? Because voltage and current. If you double voltage, you double current, right? You understand that? I can put that on a test. I can put, if I double the voltage of the circuit, what happens to the power? And just about everybody will say the power doubles. But the power don't double, power quadruples. So that's why your low voltage devices you've got access to those plugs. Your 240 devices, you don't have access to those plugs easily, right? You understand? Because they're more dangerous. So the advantage, and AC induces a voltage. So that means I can have a motor, instead of having a connection to the rotor, I can induce the voltage into it. So all electrical motors work off the repulsion and attraction of magnetic fields. That's what they work. Well, I can induce a voltage on an AC motor. I can induce a voltage into the rotor. which generates a current. And if I can make one of those fields move, the motor runs. So AC motors are a lot less expensive than DC motors, because DC motors, you can't induce the voltage, right? You understand. So DC motors are more expensive per horsepower. But I can control the DC motor more precisely than I control an AC motor. So the advantage of DC is that we can control it electronically. In fact, we can take AC, convert it back to DC, take the DC and convert it back to AC, which is, if you've got an inverter in your car, it's got a device in there that takes DC and converts it back to what? AC. Like I tell it, my wife in her van, she's got a 115 volt plug, a standard plug in her van. So she's got an inverter, but we're doing it what? We're doing it electronic. So we can do relays, don't care. It can do logic with AC, it can do logic with DC. If we do it with semiconductors, guys, semiconductors is DC. They work DC. So everything inside this computer is DC. Everything's in there DC. Because I can electronically control it, right? And I'm doing semiconductors. But I gotta, what's this guy right here? Well, this is a power supply. What's the function of this power supply? Converts, steps it down, but it also converts AC over to regulated DC. So this is why all your electronic devices have to have a power supply. They either run off batteries. Batteries create DC chemically, right? You understand? Or they run off of AC, and then they have a power supply inside the unit that you don't see. So you don't see the power supply inside this oscilloscope, but there's one in there because this is an electronic device. So it runs off of what? DC. Now the first logic they did, so when we get to the logic that we're dealing now, if it's not relay logic, if it's semiconductor logic, it's going to be DC. So diodes, we got all shapes and sizes. The size of them determines on how much current they can control. So if I'm not controlling a lot of current, then these little diodes, the diodes can get extremely small. But you can tell the cathode from the anode. So here's some diodes on this printed circuit board. So here they are right here. Yes, these are all, oops, guys, these are all diodes. Now you can see the stripe around one side. So that stripe indicates that that lead on that side right there is the cathode. So the other lead has to be the what? Anode. So these are all diodes.
So the black ones, right?
These black
ones. The beige ones. Oh, those are resistors, right?
Yeah, these are resistors. And these are color coded, right? But all the diodes in here that you can see, you can identify the cathode and the anode by the what? By the stripe. So the stripe is the cathode and the other end is what? Anode. Now these are integrated circuits, and these are what we're going to go to here before long. This one, it's big enough. If I went, we got some of these over there, but it's got the little diode symbol on the side. You can't see that. But notice there's a stripe, there's a stripe. Now these are the ones we're going to be using. We're going to be using one called a 1N914. Even though we could use some big ones because we're going to be doing logic with them, but they're going to have a black stripe around one side because they're glass. They're inside glass. Are we okay? Yes? No? Check valve, not a perfect short. We're using silicone, so it drops around 0.7 of a volt. Light emitting diodes or LEDs, theirs around they're forward voltage. They're creating energy, so their voltage is a little higher. It's like around 2 volts. They're not perfect, so they do have some resistance. You can see there's no semiconductors have resistance, so if the current goes up, they're going to drop a little voltage. So around 0.7 of a volt is what we use this for a rule of thumb. Yeah, it's supposed to be and, it's supposed to be and, it's supposed to be AN, not AN. Y'all never make that mistake, do you? I do it all the time. Thank you. I don't know, tell me how many times I've used this slide in how many classes. It always amazes me, you know, you'll use a class, you'll use slides for years, and all of a sudden somebody will say, well, that word's spelt wrong, or that's, you're using form instead. That's one of my words, form and from. I'll transpose the R and O inside that thing all the time while I'm typing. So these are two logic gates with nothing but diodes. And what we'll do is we'll come over here and we're going to come up here and we're going to set up a table. So what we'll do is we're going to come up and give these inputs names, A, B, C, and we'll call the output is on the right. This is the way we draw schematics in the U.S. Inputs are on the left and outputs are on the right, right? The schematics are drawn that way. And what we're going to do is we're going to figure out how this thing works. So what we're going to do is I'm going to come up here and I'm going to put plus 5 volts over here. So right off the bat, I have my positive on my anode, right? Y'all understand that? So what are we looking for on the cathodes? We're looking for a lower voltage, right? 0.7 of a volt, but we're going to put a lot less lower than that. So what we're going to do is I'm going to come over here and what you need to do is imagine a switch. And I'm going to either switch this input up to plus 5 volts, or I'm going to switch it down to a circuit common. Not an open, it's going to have to switch down to a zero, what we call a zero. So we're going to say that plus 5 volts equals a binary 1, and then 0 volts equals a binary 0. Does that make sense so far? Okay. So I'm going to come up here and let's say all these switches I have open. So what I'm going to do is I'm going to erase this, and what I'm going to do is I'm just going to put this up here to 5 volts. So let's say we start off with, we're going to set up a table. So I'm going to come down here and say A, B, C. I'm going to put these on the left because that's where my inputs are at. And then over here I'm going to put what's going to be on the output. So instead of writing 5 volts, well, let's do it that way first. So let's say the first thing I come over here and I put all zeros over here. So is this diode, is it going to be on or off? I have 5 volts pointing toward the cathode. I have 0 volts on the, I have 5 volts pointing toward the anode. So I have a plus there, right? You understand? I have 0 volts. Now don't think of 0 volts as being as no volts. 0 volts is a 0. So I've got this pointing to 0 volts. So it's a guy forward bias. Is it on or off?
Oh.
Huh?
Oh. You said it took
Is the cathode negative in respect to the anode?
Yeah.
So you're saying that plus 5 volts is not positive in respect to 0 volts?
Yeah.
Okay.
Hold on, see.
So is it forward biased? Is the anode positive in respect to the cathode? Yes. Here's the anode. I got a positive sign on the anode. There's that 5 volts up there, right? Pointing toward here, right? This is 0 volts, or it's not no voltage, it's 0 volts. There's a big difference between no voltage and 0 volts. So what that means is, if I came over here, I'm gonna take this as my reference. What I've got now, guys, is I've got a power supply up here like this, and this right here is my common. So that negative is going to be 0, right? You understand? So is this guy forward biased? Okay, so if it's forward biased, it's going to be what? It's going to be on, right? You understand? It acts like a closed switch. So if it acts like a closed switch, what that means is it's technically going to take this 0 and put it there. Now it's not really 0. It's going to be about 0.7 of a volt. So this output's going to go to 0.7 volts. Is this guy right here forward bias? Yes, it's what? It's on. This guy right here is on, right? You understand that? So the output's going to go to, we'll call it a 0. Are we okay? That makes sense so far? Any questions? For some reason when people see, and that's all you're looking for on a diode. So let's say I come over here and raise A. Let me change this so our numbering system will look okay. What I want is I want the I should have left that alone. I want it to look like a binary number, A, B, C. But what I'm gonna do is I'm gonna put A on this side. So what I'm gonna do now is I'm gonna come up here and I'm gonna come over here and I'm going to erase that and put plus 5 volts on A. So is A going to be on or is it going to be off? It's going to be A because you got 5 volts. In fact, as soon as this guy turns on, it's going to put a negative in respect of it. This guy here is going to be off. This guy here is still going to be what? On. This guy's going to be on. So we came over here and we have this. But that output would still be a what? 0 because of the other two, right? You understand? Are we okay? No, it can't be a 1 because this guy right here is turned on. If it's turned on, that 0 is passed to right there. And this guy right here. So the only way I'm going to get a 1 on the output is if I come up and put what on all my input. No, I said we'd use, okay, we can put binary. I said I was going to put voltage over there, but we can put binary since we say that's what it equals to. I understand now. Are we okay? That look better? Okay, so what would be the next combination? So I've got this guy here would turn back what? On, right? I'm gonna take these off over here because we can understand now. So we look at our chart. This guy right here would be on. This guy here would be off. This guy here would be on. But anytime I've got one of these on, then my output's going to go to a 0, right? You understand? So we could fill in the chart. So let's do, I'm going to get it up so I can do more. C, B, A, X. So 0, 0, 0 would give us a 0. A 0, 0, 1 would give us a 0. A 0, 1, 0 would give us a 0. A 0, 1, 1 would give us a 0. A 1, 0, 0 would give us a 0. A 0, 1, 0, 1 would give us a 0. I'm going to have to skip over this. A 1, 1, 0 would give us a 0. And then a 1, 1, 1. Now you got all these guys would be what? Off. And now the 5 volts can come over here and go off. So a 1, 1, 1 would give us a 1. So I had to have all 1s to get a 1. Well, we're saying 1. All off, you're right. But here we'd say all off, right? Or all 1s to get a 1. So what type of gate would this be? And, you're right. Good. This is an and. So when I look at the output of a gate, if I say all, then this is going to be some type of and, right? If I say any, it's going to be some type of or. Are we okay? That makes sense? So that's an AND gate. That's an AND gate. And what could I do? I could come down here and put another diode, and instead of having a 3-input AND gate, I'd have a 4-input AND gate. This guy, by the way, we refer to this as a truth table. What a truth table does is it shows us how the output responds to every possible combination I can put on the input. Now notice all we're doing on the input is counting, right? You understand that? And you can tell how many entries you got in it. So I have 3 bits, and you can tell how many entries you have just by taking the base. This is base 2, and then raising that to the number of inputs. So here this will be 2 raised to the 3rd. So that means I have 8 possible combinations on my input. 1, 2, 3, 4, 5, 6, 7, 8. So if I went to this one, how many would be on my truth table? Well, now I've gone to the 4th, so I'd have to have a table that has 16 entries in it. If I went to 5 inputs, I'd have to have 32 entries in my truth table. Truth tables are really nice, but they get cumbersome the more inputs you're trying to, because what a truth table shows you is what happens to the output for every possible combination you could put on all the inputs to the circuit. By the way, what we do is we refer to these as gates, so we'd call this an AND gate. So basically it takes all ones to open the gate and let the one get out, right? Understand? If I put any 0 on the input, then the gate's going to be closed. And that's basically why these things got the name as a gate. Truth tables are nice. So what we'll do is we'll look at a 2-input AND gate. We'll look at a 2-input OR gate. The gates, while we're learning the gates, we're going to use 2 inputs because we're going to have to develop these truth tables. And that way we'll only have 4 entries in our table, right? 0, 1, 2, 3. Well, what you got to understand, I could have, how many inputs could I have over this thing, and it would still be all highs to get a high? A lot.
Unlimited.
Yeah, basically unlimited. You're exactly right. So this was nice, and this was the first gate. So we ran into a computer that uses this, where they spread the OR gate over multiple circuit cards, but each one of them just used its own little diode. So what do you think we should expect out of this one over here? If this was an AND, then what do you think we should expect out of this one? Hopefully this is an OR. Notice the diodes are switched around. The ORs are just opposite the ANDs. So A, B, C. A, B, C. We'll do a truth table. Have to move it up further. And we'll call the output X. Now, when you get into circuits, when they start dealing with giving these signals names, they're going to be actual names. Normally, when we teach it, we use letters of the alphabet because it just makes it legal. And what we'll do is our inputs will start at A and run towards Z, and our outputs will start over here on high letters. Does that make sense? So I'm going to come up here with zeros over here. 0, 0, 0. Right? Over here I've got a 0. So is this guy here on or off? Yeah, I got to have a plus on this side, right? So this guy here would be off. This guy right here would be off. This guy right here would be off. So that guy would be that, right? Understand? And all I have to do is just do one of them. So I'm going to come over here and I'm going to put plus 5 volts right there. I'm going to put 0, 0. Here's 0. So the cathode's pointing towards 0. The anode's pointing toward a plus voltage. So this top one's going to do what? It's going to turn on. It's going to let this 5 volts come through. Right? You understand? So we'll get about 4.3 volts over here. We won't get 5 volts because the diode dropped 17. Now this guy can't come on because this has got a plus on that side and it's got a, right, you understand? So this guy right here is going to be off. This guy right here is going to be off. But here when I came over and put this on there, my output went to a what? To 1. You okay, Brian?
No.
I can tell by you.
Because I'm kind of confused about how you get the 5 volts to 5 volts. Because I see how I got 1 kilo ohm from the ground.
Yeah, but I can't connect the ground because if I didn't have a resistor, and just like here, if I came over here and made this a 0, by the way, technically we call this a pull-up resistor. Call it a pull-up resistor. Because over here on this left side, that resistor is providing the high. Right? You understand? My diodes are not providing the high because when I put 5 volts, they turn off, right? So technically we refer, this is the, what we call a pull-up resistor. And what do you think we call this one? Pull down, good. Okay, so imagine the diode. We know it's not exactly an open switch, a switch, right? You understand? But we can talk this. So let's say I come over here and I have a switch. And then I come over here and connect that directly to plus 5 volts. And then I close that switch and this right here goes to ground. Well, I just created a short circuit. Right? If I put a resistor right there, that means when I open the switch, then over here I get plus 5 volts. If I close the switch, that's going to connect to the bottom of that resistor, so here it would go to 0 volts. So that pull up and pull down resistor allows me to bring a true 0 in, or what? Now listen over here, what we have to look for is what I'm trying to do is I'm going to come over here and hook this up to plus 5 volts. And over here, if I didn't have that resistor there, that right there would be hooked to common, right? You understand? I close that switch, I have a short circuit. If I put a resistor right there, if I close that switch, I get plus 5 volts. If I open that switch, if I close the switch, I get plus 5 volts. If I open that switch, there's no current flow through that resistor. The resistor's not going to drop any volts, and it would give me 0 volts out. So we got to have that pull-up resistor on my AND, and we got to have that pull-down resistor on my OR. So what? So that means I can put plus 5 volts at the top and not connect it to ground. Over here, we're putting ground and not connecting it to plus 5 volts. So we got to have that pull-up resistor on these gates right here. Does that make sense? Because right now, this is and you don't have to say it's got to be 0. To forward bias a diode, the cathode has to be pointing toward 0 volts, and the anode has to be pointing toward 5 volts in our situation. It don't have to be connected to it. All it's got to do is be pointing toward it. So right now, my cathodes are pointing toward 0 volts. So they're pointing toward the negative. So if I come up here and put plus 5 volts over there, now I've got my anode pointing toward the positive. My cathode is pointing toward the negative. It will turn on that diode. As soon as it does, this 5 volts would come flying through. If it was perfect, it would be 5 volts. If I had that connected directly to ground, as soon as we put that 5 volts on there, I'd blow a fuse because that would be a short circuit. But I'm making it go through what? To a resistor. So as soon as I put that 5 volts on there, this guy's forward bias. It's only going to drop 0.7 of a volt, so my output would go to 4.3, and then this current right here would only be 4.3 milliamps, which is not much at all, right? You understand? So a 1K resistor in a 5 volt logic, we're going to be dealing with 5 volt logic. We call it TTL, transistor logic. We'll learn that, but it runs off a 5 volt supply. So anytime we need a pull-up resistor or a pull-down resistor, odds are we'll use a 1K. Makes it real easy to calculate, right? At 5 volts, that's only 5 milliamps. I square R, right? That's still not hardly any power at all. But what happens, if I have this 5 volts right here, this guy turns on. Even though these two are off, as soon as this guy turns on, that makes the cathode positive in respect to the anode, and these guys turn off, right? Y'all understand that? And we can see what happens now. So to get this guy right here, anytime I have 5 volts over on any one of these leads, this output's going to be a 1. Yeah, so that means I can come up and go through all the combinations. So that's 1, 2, that would be 3, this would be 4, this would be 5, this would be 6, and this would be 7. for all my combinations, this would be a 1 out here. So this would be the truth table for a 3-input OR gate. That's right. Over here, my cathode, my anode is pointing toward the positive, and on an OR gate, so over here, any 0 will turn this guy here on. But the problem is, if it turns it on over here, that's going to bring that 0. If the diode is perfect, that's going to bring that 0 and put it right there. If I didn't have that if I didn't have that pull-up resistor there, what would happen? We'd have a short circuit, right? Does that make sense? Over here, any 5 volts is going to turn it on. And if this thing was perfect, that means that would put 5 volts right there. So over here, any 5 volts over here on any of these inputs would turn this guy here on. So there's an OR gate. Now we got 2 more logics we got 3 actually we're going to look at. So the 3 options we have is the 2 we just looked at, and OR. And then we got a NAND, NOR, and NOT.
But we only working with and.
Now.
And or.
Now to do with diodes, we can't do an we can't do a NAND and we can't do a NOR with nothing but diodes. We have to add a transistor to it. We have to add an inverter. So we have to invert the output somehow. And we can't invert change the state of it. We can't invert that with a diode. So the only gates we got available with nothing but diodes and resistors are ANDs and ORs. To get a NAND, we have to have a transistor, and we'll look at that we'll add a transistor. Okay. We okay? We call them actually called bipolar junction transistors. We got 2 types of transistors. We have what we call a bipolar junction transistor, which are the ones we're going to. These are the ones we're going to deal with. Most people call these BJTs. These are 3-terminal devices. 3 lead. They got 3 leads on them. So they can come in all different types of packages. I'm trying to see some that's really, really small. So this is a transistor right here. And when I flip it over, you can see where it comes out the other side. You only see 3 pins, right? So there's 3 pins. So that's definitely a transistor. And we'll look at some of the packages these things can come in. These are all transistors. Yeah, these are all transistors. This we don't know. I have to look at the number. Because we do put some integrated circuits inside these packages right here. These are called TO package. They're called transistor outline package. That's just because the transistor was the first one to use that. But any circuit that will fit, that only needs 3 pins, will probably be in one of these packs. So we have triacs, we have SCRs, we have voltage regulators, we have a lot of other circuits that use this, but we still call them a TO pack. And I'll give you so this is what we call a TO220. But over time you would learn them, but until then you'll need to look them up on a chart that shows you what they look like. Let's see if I can see them. This is a transistor right here. It's just this is a TO92. This is a pack that this is the size of the transistor we're going to deal with. This little guy right here. That's it. I'm trying to find some little bitty transistors. These are transistors. If my camera will focus on it. These are all transistors right there. These are surface mounted. Y'all can see the little pins. I'll pass these around. These guys have a lot of technology that we could damage them just by handling them. But all these boards, these are not, we don't use them anymore. This is an old video adapter. This is back in the day where all your computers were used big motherboards and you plug different cards in them to get what you wanted. This was an old video adapter. That we still use this interface. This is called VGA, by the way. This is still used a lot. This is the memory on the video card down here. These are different integrated circuits. But these are transistors right here. Anything that's got, can y'all see the little 3 leads right there? So transistors are current valves. They control current. We can use them to precisely control the current, or we can use them as switches, which means we can turn them on or we can turn them off. And they work really, really well. When we turn them wide open, they drop less than a volt. They drop less than 0.7 of a volt. And they're really, really fast. Oops, I keep hitting the wrong button here. We have 2 types of BJTs. One of them's called an NPN and a PNP. This is the one we're going to be dealing with in our class right here. And it's a 3-lead device. So we start off with this, and then we have this, and then one of the leads has an arrow pointing out of it. Everybody okay? Now, then we got another symbol that we just look at. So notice on this one, the arrow's pointing out. On this one, the arrow's pointing in. This is not pointing in. That's an NPN. This is pointing, we can't do that, but this one's pointing in. So this is a PNP. Now what this is doing is this is telling us the polarities we need to turn this thing on and turn it off. So this is called the emitter. This is called the base. And then this lead right here is called the collector. Now to turn it on, we're looking at the base and the emitter. And it tells me that the base has to be positive in respect to the emitter to turn this thing on. And we'll talk about the collector in a minute. Here's your valve right here. Here's the knob right here. So this is my control of the valve right here. So this is your control. So I'm going to use that to open the valve or close the valve, but I'm not going to grab it with my hand. I'm going to do this electronically, right? You understand? That's my control. And here's my valve right here. So what I'm doing is I'm going to use the base to control the flow between the emitter and the collector. So we're going to use it as digital. We're not going to use it as an amplifier. We're going to use it. Well, that's not true. These guys are current amplifiers. We can make them appear to amplify voltage by running them through a resistor, running the current through a resistor. But these guys right here are current valves. And hopefully y'all understand how a water valve works. What can we do with a water valve? But I'm coming up here, I'm using a little old tiny handle. I could turn the water on my sink wide open, and I could take my hand out there and try to stop that flow, and I can't stop that flow. I just squirt water all over the place, right? You understand? Anybody tried to stop the flow on your hose pipe out there? You can't hardly do it, right? You understand? You can cover it up a little bit, but you can't do what? You can't stop it because of that pressure. So what we do here is that base is like the valve itself, the control for the valve, which I can use a very little force on that valve to control a lot of flow of water, right? You understand that? And it's just like a water valve. What determines the size of the water valve? It depends on how much flow it's trying to control. If it's trying to control a lot of flow, the valve's got to be big, right? You understand? If it's got to control a little flow, then the valves can be very, very small. So what I do is I put a real small base current in there to control a lot of collector to emitter current, or emitter to collector current. Very small base current. But the base is the control. If I can put enough base current on there, this guy here is going to turn wide open. It's going to let the maximum flow go through. So we got 3 regions we can operate this thing in. One of them is called cutoff. That's when we put 0 base current in. And then we got what we call saturation. That's when the valves turn wide open. This is the 2 regions we're going to use in this. We're either going to saturate this sucker or we're going to cut it off. Now for amplifiers, like in your car, they run it as an act. So here it acts like an open switch. It's not an open switch. Here it acts like a what? Here it acts like a closed switch. In the active region, it acts like a rheostat.
So how does it cut off? Like an open switch, you saturate it as like a closed switch. You saturate it, close, got let everything flow through.
Well, that's what a closed switch does.
Okay. Oh, I'm sure. Okay.
So technically, a closed switch drops all the voltage when you have it open, right? You understand, and don't allow any voltage, don't allow any current to flow. A closed switch drops 0 volts because it's letting all the current flow with no resistance. Now, a transistor will always have resistance. So when we close that switch, it's going to drop. Saturated transistors drop around maybe 100 millivolts, which is not much at all, right? So what that means, if I put a 0 over here, then this sucker is going to turn off. No current flows through it. If I come over here and put a 1 over here, we're going to have to put a resistor, guys. We'll talk about that later. Then this guy's, we're going to put enough, that 1's going to provide enough current to saturate this thing, and the maximum current's going to flow. The only thing that's going to control that current is what load you hook this thing up to. It's got to be hooked up to some type of load, right? You understand? So we're not going to take this guy and hook it directly to a plus voltage, because that way when it turns wide open we'd have a short circuit. So we got to have some type of load in the circuit, just like a switch. A switch controls the load, right? You understand that? So I'm not going to take a switch and put it between my 2 lines. I'm not going to come over and do this, even though some people do this on motor control. I'm not going to do that, right? Because if I close that switch, I have a what? Short circuit, yeah, short circuit. So what that means is we're going to always have some type of load right there. Normally we connect, on ours, we're going to connect the load up here in the collector. Now this is where it gets confusing, is that your collector has to be reverse biased. And it has to be reverse biased. So let's hook this up. Let's see if I got a circuit. Oh, okay. So what I'm going to do is I'm going to put a resistor up here. We'll come down here, we'll connect this to common. And then right now I'm going to put a switch over here. And I'm going to either switch this up to +5, or I'm going to switch this down to common. Now the problem is if we look this is a little diode right there. And what would happen if I close that switch, it would be a short circuit, right? You understand that? So we have this base resistor in there. If this is 5 volts, my base resistor is going to have to drop 4.3 volts. That makes sense? Well, the diode, we talked about this a while ago. If this is a silicon diode, it's going to drop 7 volts. Kirchhoff's voltage law says the sums of the voltage drop in a series loop has to equal to the applied voltage. If this guy right here is dropping 7, I put 5 volts up here. Here's my current path. Of course, it's going up the other way, but here's my current path. Comes up here, goes up through here, goes like that. So that's a little series loop, right? You understand? Kirchhoff's voltage law says it has to drop the applied voltage.
Okay.
So we have to size a resistor to drop 4.3 volts. 0.7 would be for the P-N junction that's between here. So that's a P-N, we call that a P-N junction. So that's basically a diode. Everybody okay? Are we okay? So then, it's just a series circuit, guys. So if I'd have came out here and I drew this circuit right here, I said, okay, I got 3 resistors. I'm going to come over here and I got a 5 volt supply. This guy right here is dropping 0.7 volts. This is plus 5. How much voltage would have to be dropped across that resistor? 4.7. According to Kirchhoff's voltage law. Kirchhoff's voltage law says the sums of the voltage drop in a series path has to equal to the applied voltage. So what happens is this junction right here drops what? 0.7 volts. I'm putting 5 volts on there. Now what would happen is I've got the cathode, it says it needs a P, I've got it pointing toward the P. I have an N, this points toward the N, so that would create a path right here. Now what happens is that this guy right here has a lot of current carriers in there. This guy right here has very few. So what happens is these current carriers get bogged in right there. So what I'm going to do is I'm going to come over here and I'm going to put a real high potential over here. Let's say over here I put 15 volts. So I've got these electrons coming in here. It says I can flow this way towards 0.7 of a volt, or I can flow this way toward 5 volts. Where's those electrons going to go? Yeah, over 95% is going to travel this way right here. Now, when you take solid state, if you do take solid state, we're going to give that in more detail. But those electrons are looking for a positive, right? You understand? They're looking for a positive. What happens is that this base basically crams those electrons coming out of your emitter. It crams them into a spot, because not many of them can go out the base lead. And what are electrons looking for? Where they're looking for a positive. So if I put a big positive up there on the collector, what's that going to do? It's going to pull 99% of the electrons through there. So what we're saying is I might put over here, I might be providing 1 milliamp. Over here, I might be getting 100 milliamps of flow over there. So what we have to do is your collector has, even though it's got an N, your collector has to be reverse biased. So notice up here we have a P, right? You understand? Relative to 0.7 of a volt. So basically your collector junction is reverse biased. But whether you understand it or not, we have to put a big positive on the collector or a positive on the collector. The emitter has to be negative in respect to, right? You understand? And then we can turn this thing on or off. Now, if I come over and switch this down right there, this and this is connected together. My base current goes to 0 milliamps. If my base current goes to 0 milliamps, then the transistor is going to turn it off. So it's going to act like an open switch. We're going to show y'all guys, we use this saturated switch all the time. We called it a saturated switch, but actually we're switching it between what? Cutoff and saturation. So that's what we're doing with digital. We're doing cutoff saturation. And we're using this guy because my input has a supply of very low current to control a lot of current on the output. So on the gates we're using, a high requires around 400 microamps. On the input. On the output, it's going to be controlled in up to 16 milliamps because of transistors. So what's nice about a transistor, it takes a very small base current to control a very comparatively large emitter to collector current. You just say collector. Okay, guys, y'all go ahead and take another break before I burn y'all out. No, a P&P is predominantly for negative power supplies. NPN is for positive power. Yeah, I will. So we're going to be dealing with positive power supplies this semester. So that's why we're going to. So a P&P, the base has to be negative in respect to the emitter. A NPN, the base has to be positive. So if I was going to do this with a P&P, same circuit, then I'd still have to have that resistor there. But what I would be doing is I would be switching this from a negative 5 volts common, and up here this would be a negative 15 volts. And that would be for a P&P, but the circuit would work the same. This would still drop 4.4 volts. This would still drop what the difference between this and ground. This is why we had to have that resistor, because if I turn that transistor on wide open, it acts like a closed switch and we'd have a short circuit. So this is that, if it's acting like a switch, we got to have some type of load in a circuit, right? Y'all understand that? So what we're doing now is instead of using that mechanical switch in that circuit, what we're using now is we're using a transistor. This would be 0 volts over here. Make sense? So over here, this mechanical switch I'm closing. What we're doing with the transistor is we're closing and opening the switch with a very small DC current. So what happens when I switch this thing up, then this guy right here is going to drop 15 volts, and this guy right here is going to drop 0 volts. It's like a closed switch, but it's not going to be 0 volts. This is actually going to be around 100 millivolts, which means this guy here is going to drop 49.9 volts, right? So for all practical purposes, now a switch would drop 0 volts. A transistor can't, because it's running through a semiconductor, and it has resistance. But for this to work, I would have to come up here and this would have to be my positive over here. But this would be replacing the what? That switch right there in a circuit. So every control device is in there to control a load, right? You understand? So we're going to have to put these loads up somewhere inside our transistor. So we could use this to turn on a light bulb. And this is the next one we're looking at. But these transistors, they allow us to, I'm controlling amps of current over here. You know, on your car, you're used to your car headlights was controlled by relays, and they probably still are. But you're using a little old tiny push button, you know, you control your TV. Your TV might be pulling 100, 200 watts, and you go over there and touch a little old touch sensitive button to turn that dang thing on or off, right? You understand that? So you're using just the voltage coming off your fingers, and y'all know we do that, right? So thank goodness we wouldn't have these cell phones if it didn't work like this. These touch screens. Go between classes. So your touch screen on your phone works off of something called capacitance. No, I'm not. This is not class. This is just talk for y'all that want to stay in here. It's capacitance. It's new. It's giving it capacitance. So all the touch screen on your TV, on your cell phone or your tablet is just thousands of little capacitors. And when I come in, it's in a matrix like this. So when you slide your finger across there, basically you're touching a little capacitor and it generates an AC signal. So this is what you're doing when you get on the back of on your front of your TV. It's got that little flat button. You just touch it. It's just picking up me. 60. This is 60 cycle, right? This is me. And what that means is we can literally transfer this magnetic lines of force. It's probably not going to do good on this one because it's shielded. I need another piece of line. These GoPros are shielded. It makes it hard to pass this through. So this is the way you're receiving stuff. So we're transmitting over here. So this is one thing right here, right? You see that? So this is the antenna out there for your cell phone. Then your cell phone's got an antenna in it. So what I'm doing, I'm creating a capacitor. So notice they're not even connected together. So where's this information coming from? It's coming through the air, right? We call this the capacitor. And that's the way this is the way all your broadcast stuff works. Your cell phone. We have these cell towers up there. They're shooting out. They got one of these things sticking up in the air. You got an antenna. If you ever tore a cell phone apart in the back, usually it's got a bunch of wires wrapped around it. It's nothing but an antenna back there. And it's just picking it up like that.
You said it's serial.
Yes, it's definitely serial. Because we only got one media. So media is what information flows through. Well, air is only one media. So all the information coming to your cell phone. Wi-Fi is serial. Well, also a wired Ethernet is serial too. because it saves so much money. I forgot it, originally when we hooked up our Ethernet, it was all wired. We got wires running all through the ceiling in here because of wired internet. And now just about everything's gone wireless. Of course, I don't like wireless. If I'm going to do anything important, I usually use hardwired. So, I can't say that. This is shielded all the way up to the end, so it really makes it hard to pick. So the only thing I'm picking up is up here at this very little tip right here. So if I had a regular wire, this would pick up better. So this is the way your touch screens and everything work. They got a bunch of capacitors in there, and when you touch them, it picks you up, right? You understand, depending on a metric. Now that one over there on the manufacturing line, it works off resistance. It's got two resistive screens, and you have to press on those because when you're out in a plant, these guys got gloves on. So these capacitive screens only work if you got something that creates capacitive, right? Yeah. So that's why this works on this guy right here, but it won't work on my cell phone because of the way the screen's set up. But y'all ever tried to do can't do your cell phone with gloves on, right? Now they do sell some gloves that's got the little tips on them.
Like, so how would they have made gloves?
Well, they got carbon fibers in them, so it lets the AC come through. So you can buy gloves that you can use with your cell phone. But that one you can use.
That's within carbon fiber.
Yeah.
Yeah. Now, what a bipolar transistor has, it has a rating that we refer to as beta. And this indicates the current gain of the transistor. It has no units. It's just a multiplier. When we look at the data sheet, it's going to be called H sub FE. Books teach beta, but you can go into the data sheets and you'll never see the term beta. So these two guys right here are exactly the same. It's the hyper transfer ratio with the emitter common. So that's what it was.
I thought it was high frequency energy. Man, no.
So that's a symbol for a light bulb. And then we're going to come over here and have a little tiny switch over here. And this is going to go up to plus 5 volts and that. Now, what are light bulbs rated in? Watts. Except your little small one, they're usually rated in. They're rated in, just about all electronic devices are rated in at least 2 different things. So light bulbs are rated in voltage and watts, right? How much voltage you need to put on across them, and then what wattage they would do. Unfortunately, transistors don't work with wattage, it works with current. So if I had a 10 watt light bulb at 12 volts, a 12 watt 10 watt light bulb, then I would be equal to 10 divided by 12, right? You okay? Did I lose anybody? So P is equal to D times I, or I times D. So I would be equal to P over V. So what we did is we have a 12 volt bulb rated at 10 watts, right? And then we're trying to figure out what I need to do to turn this thing on with a digital switch. So what I would do is I would come over here and I would say my I would be equal to what? About 80 milliamps or something.
.8.
833 milliamps. So it would work fine off of 8 milliamps because they understand that the voltage a lot of times is not exactly right. So let's say we need not 8 milliamps, right? All right? Is it 8 or? Okay, so we're going to turn this thing on with a 5-volt supply. So what I need to do is I need to know how much base current is required to saturate this thing. So what we would do is we would need to know this guy right there. We'd need to know the beta of the transistor. Because what I would do is I would say if beta is calculated by IC over IB. So that means if I knew what IC was, which is what we know, right? You understand that? Okay. Then I would know IB would be equal to what? IC divided by beta, right? Okay, are we okay? And I don't want to get these base currents and beta confused. So where are we going to find the beta of a transistor? In the data sheets, right? So we have data sheets on all these. These transistors are going to be given numbers. Normally, and this is not always true, but most of your transistors start off with a 2N. This would be like the model number of a car. So it's just like when you go buy a part at AutoZone, right? What's one of the first things they ask you? What's the model? What's the credit look like? They only do that at the cash register. So normally you walk back to the desk right there and get your part. So they won't know the make the model, right, of the car. So that's basically what we're going to do here. So we got these, and what they do is they go in these big old specification books, right? You understand? They look up that model number. Then they've got all kind of part numbers depending on what they do. A lot of stores, like Walmart, has that little punch thing that you just come in and you start punching, right? You understand? You can, that never works, right? Yeah. Isn't that what they got back toward their oil filters and all that kind of stuff, or they go back to the books? But even if you have the big books, you look it up. You look up your make of your car, then the model of the car, right, then the year of your car. Well, most transistors, the model number or the part number starts off with 2N, and then they'll have a group of numbers that you would look up. The one we're going to be looking at is a 2N3904. That's the one we're going to be looking at. And this is not always true. We have some TIP models that are registered. These are what we call JDEC registered components. Joint Electronic Device Engineering Council. What they do is they're basically, they're like NEMA. Y'all know what NEMA is? National Electrical Manufacturers Association. They standardize electrical things. So originally when they started sending power into the house, they had to come up with some way to get from the power to the device, right? You understand? So we could hardwire them, but that didn't work very long. They came up with receptacles. Well, the problem is all these different companies were just making up their own receptacles. And what the plug looked like and what the receptacle looked like that the plug plugged into. Eventually they said, well, there's got to be a better way. We need to set up standards. So all these manufacturers that were manufacturing these things got together and formed this thing called NEMA. So NEMA standardizes basically the way electrical devices connect, and also frame sizes. So the frame of a motor, how big is it? How far is its feet apart? So that means if I want to get a motor, how long is the shaft? Then if I want to buy a motor, I don't have to buy it from the company that I get it from. All I got to do is get one that's got the same horsepower rating, current, and the same NEMA frame, right? You understand? So it means I can bring that same NEMA frame in and mount it into my exact spot. So these wall outlets that we see around here, I don't see them on the side, back there. These are NEMA frame. These are NEMA outlets. They're NEMA. Huh? Okay. So that's a NEMA 5-20 frame. That's a socket. And it's standard. It's an industry standard. So now I don't have to go all over the place to find a plug that plugs into that thing because it's a NEMA plug, right? You understand? This is a 20 amp plug. I don't know if y'all can see this or not. But can y'all see the little blue lane right there? So if you had a 20 amp device, it would have a little L right there, and it would require a NEMA 520. A NEMA 515 is what you probably have at your house, which is a 15. So you can't take a device that's designed around 20 amps and plug it into an outlet that's rated at 15. But you can take a device that's rated at 15 and plug it into a plug rated at 20 amps, right? Does that make sense? But NEMA made these standards. Well, JDEC has standardized packages. So they've standardized packages. They've standardized part numbers. So that means I can put out a transistor that's got a 2N3904. As long as I meet the NEMA, the registered standards for that transistor, I can use the same part number. So a 2N3904 is basically open technology, which means if you got the capacity, if you got the equipment, you could put out a 2N3904 transistor and you wouldn't have to pay anybody. That makes sense? And the packages the packages that we put these things in are standardized packages. They're all JDEC registered packages. So if it's JDEC registered, it means it's open technology. So that means anybody can use that TO220 pack. If their circuit only needs what? 3 pins. And dissipates a certain amount of power. So it means I could look up a data sheet for a 2N3904 on all kind of places. And one of the things it's going to tell me the H sub E of the transistor, which book's called beta. So, but I've never seen a data sheet that calls it beta. They call it H sub E. So it means if I know this guy here, so the typical beta of and we'll talk about this later on, the typical beta of a 2N3904, or the beta we're going to use is 30. So that means to calculate the amount of base current I would use, I would say my IB would be equal to 8 milli divided by 30. And what would that give me? Is that 266 micro? So what I'm doing is I'm able to use microamps to control milliamps, and that's the function of the transistor. Okay. So what I'm going to have to do is I'm going to have to choose a resistor right here to drop how many volts? 4.3 volts. Y'all follow so far? At 266 microamps. So R is equal to V over I. So R would be equal to 4.3 divided by 266 micro. So R would equal to what? So y'all doing some little engineering. These guys are pretty easy to do. Nobody ain't got it yet? Wait, what's that? Probably got a fraction out beside it. So what did you do? Did you round up or round down? Why did you round down? That's right. By the way, this resistor, we always round down. And then we round down to the next standard value. So what we'll do is, one of the things that we're going to let y'all know, did they give that out in DC, the resistor standard value? Did y'all get that in DC? They need to do that. Because they just don't make resistors. Resistors have standard values, right? You understand that? And I could use a rheostat and get any that's bigger than what I want, and I could literally get any resistance I want to. But if we looked up a 10K rheostat, quarter watts, it's going to be about $5. If I looked up a quarter watt resistor, it's going to probably be around a nickel. But it's going to be a standard value. So they just don't make all types of values of resistors. They make standard values, right? So what we do is we do all the math and we decide on a value, and then we got to choose a standard value. So it's very seldom an electronic circuit operates exactly the way it's designed. But so every circuit has tolerances, right? Let's see if I got the standard resistor chart in this one. But I'll run it out for y'all. Originally, one we got was EIA, which is the Electronic Industries Association, which is, by the way, has been disbanded. So I don't know who's handling this now. I know TIA is handling the communication standards that EIA came out with. We don't hardly ever see 10% resistors anymore. Usually the ones we see are 5%. So you calculated 16K, so I would use a 15K. I always go down to the next standard, and we'll talk about why. But notice if I use highs and lows, so let's go back to just a transistor. And what I'm going to do is I'm going to come up here and let's do 5 volts right there. And I'm going to take my output right here. Now what you got to imagine is that transistor is going to act like a switch, right? And basically what I'm doing is I'm taking my output between here and this right here is common. So that means right now with that switch open, my meter would measure plus 5 volts. Everybody understand that? Yeah. Okay. Technically a meter has about 10 megohms worth of resistance when you got it on volts. So all practical purposes, it's an open circuit. So there's a little tiny bit of current flowing through that, but it's not enough for my meter to even measure. You could do the math. So what's going to happen is that if there's no current flow through a resistor, how much voltage does it drop? None, because voltage drop is equal to V times, voltage drop is equal to I times R. Well, I could have V, I have 0, and this guy right here could be 1 megohm, and that's still going to drop 0 volts. Well, if it drops 0 volts, that means that 5 volts is not dropped. That means if I have plus 5 volts there, I'm going to have plus 5 volts there. and my meter's going to measure 5 volts. Plus my switch is open. I'm measuring across an open in a series circuit. Any open in the series circuit, the voltage appears across it. Now, why? I mean, I could come over here and I could have 1,000 resistors, right? And this right here could have, that right there could be 12 volts, and all these could be 10K. This could be 10K. And we're not going to do the math. We could. But let's say that resistor right there opens. Well, if it opens, what did we lose? Well, we lost I. As soon as I owe I, this guy right here, B is going to equal to 10K times 0. That guy's going to drop 0 volts. So that's effectively, if this guy drops 0 volts, that's effectively taking this guy and putting it right there. It's taking this guy and putting it right there. So I measure across the open, it's going to measure 12 volts. And that's why in a series circuit, if you have an open in a series circuit, the entire voltage appears across the open because there's no current flow in the circuit and nothing in the circuit is dropping a voltage. So the entire voltage appears across the open. So there's my switch right there. So my switch, I'm across my switch and it's open, so the entire voltage appears across the open. Now what's going to happen when I close my switch? Now that's going to take that common and put it right there. My output, my meter's going to measure 0 volts. So when the switch is open, I get a 5. When the switch is closed, I get a 0, right? Understand? Okay. So over here, there's my switch right there. I come over here and put plus 5 volts. If you're using the right saturates, it closes that switch, the output goes to a 0. So a 1 in gives me a what out? A 0 out. I come over here and I put 0 volts on the base. I have 0 volts on the base. I have 0 volts on the emitter. I have no difference in potential. I have no current flow. I have no base current. The transistor turns off. The transistor turns off. Now it acts like an open switch. The output would go to plus 5 volts. So when the input is a 1, the output goes to a 0. When the input's a 0, the output goes to a 1. What is this guy doing? Now technically the circuit is called an inverter, but it's doing a logic we call a NOT. So the NOT circuit has a name. In ANDs, the AND circuit is called an AND. An OR circuit is called an OR. On a NOT, the circuit is called an inverter. Now, why they did it, I don't know, but that's what it does. It inverts, right? 1 in gives me a 0 out, a 0 in gives me a 1 out. So I could take this transistor and put a transistor right here. I have to put another, well, no, I can use that resistor right there. Yeah. I can put a transistor right there. And now this becomes an AND. But I can't, because this guy inverts, right? So what a NAND is, it says all highs give me a low. A NAND. An AND says all highs give me a high. So we could create a logic gate like this. So this is the way they first envisioned it. So we started off with this. So this was around for a while. They wasn't around very long. Now the way they came up with this, they say, okay, over here, this is where this is what your inputs are connected to. This is what your output is connected to. And then this would be logic. So we refer to this as RTL logic. R, my input's on what? Resistors. My output's on a transistor, so this was known as RTL logic. And then, of course, then we went to this guy right here, right? You understand? So what type of logic do you think this was called? And so this is called DTL. That makes sense? Now we're dealing with something called TTL. So what does that mean? But what means we're going to input on what? Transistors. We're going to output on transistors. And so this is the logic we're going to be doing. Make sense? Why don't make sense of it?
I don't know.
Now these circuits get real complicated, but what you have to understand, what happened was I can make these things, I can make them physically, right? You understand? But these guys are normally in digital, these guys are not trying to drive a lot of current. So what determines the size of the valves? What determines the size of the water valve? Size of a water valve. Not the pressure. The pressure would determine the thickness. The flow, how much water or how much flow are you trying to control? If you're trying to control a lot of flow, then your pipings are going to have to be big and your water valves are going to be big. So what determines the size of a transistor? How much current you're trying to control. So that means if I can get down to a circuit that requires very, very little current, then these devices can get extremely small, right? You understand? Well, what happened in digital can't control a lot of current. On TTL, the maximum on most TTL gates is only like 16 milliamps. So it means these transistors can be extremely small. So what they did was they came up with the ability to integrate an entire circuit or to put an entire circuit on a single piece of silicon. And these became known as what? Integrated circuits. Have you ever heard that term? Or most people call them ICs. So what we're dealing with, TTL, and what you got to understand is that if it's all inside, if the entire circuit is on a single piece of a silicon wafer, you really don't need to know what's in there. Because if one transistor goes out, what do you have to do? You have to replace the entire circuit, right? You can no longer, an integrated circuit, replace an individual component. You have to replace the whole circuit. So that's what we're going to do we'll play around with some saturated switches because eventually you're going to have to drive something that's going to need a lot of current. So a TTL gate cannot turn on a light bulb, but it could output enough current to saturate a transistor, and the transistor could turn into a light bulb. So we're still going to have transistors even on computers. So we'll look at saturated switches and we'll learn how to do those. But when we get into these TTL gates, we don't need to know the circuit that's in there. All we need to know is what do I expect on my output when I get a certain input, right? So if it's an AND gate, I don't care if it's got 15,000 transistors in there. It takes all highs to get a what? To get a high on the output. So we'll look at the circuits just to try to intimidate you, but we're not going to troubleshoot it on a circuit standpoint, right? This is what we're going to troubleshoot it on. So these are integrated circuits, guys. These are called dips. And why are they called dips? So this is a package. They come in a standard package. The standard package we're going to be dealing with is they're going to be rectangular in shape. They're going to have connection points, conductors coming out the side. We refer to them as pins. You'll see why. 1, 2, 3, 4, 5, 6, 7. And they're going to be the same side of pins on both sides. And they should line up, guys, but they're not. 1, 2, 3, 4, 5, 6, I messed up. And they should line up. We call this package, we call it a dual inline package. You okay, Kelvin? We call this a wad. This is referred to as a deal. So these are deals. By the way, if you put them down on your desk, make sure you put them down with the pins down, because if you put them up, these guys are very sharp. Dual inline package. So what we got is we've got two groups of pins, and they're in line with each other. There you go, Brian. Pass these up.
Like a dash. Like, I don't know.
Yeah, you can put dashes in there if you want to, but there's no dashes up here for the acronym deal. Pass them out for them.
Everybody get one?
Everybody gets one. I think
okay.
And then if you look real close, there's some type of number on it. I've got mine drawn sideways, so it's going to be hard to write. Like an SM 7404 should be on there somewhere. It might have other letters on there, so these are all 7404.
Yeah. It's 7404.
N, yeah. Some of them has N on it, but those, we're not interested in those. In fact, we're not extremely interested in SN. Usually, these are, if it's got SN, it means these were made by Texas Instruments. It's like a MC, it means it was made by, I forgot now. So the first two letters basically tell us who made it. And then the part number would be the same, and then it'll end with a code. Are we okay? Huh? You just don't. You just got 7404? That's fine, that's the number. So we don't know who that one was made by. And so we don't know who that was made by.
Singapore.
Might be. Yeah, we got a lit magnifying glass over here, right? So y'all gonna be using that a lot. But usually what you have to do is you have to roll it a little bit so you can see the reflection. The 7404, this is what we call a 14 pin. We call this a 14 pin dip. Y'all don't believe me? 14 pins, so it's got 7 down one side, got 7 on both sides. You see why it's dual in, because they're in line with each other, right? Okay. The way we number this thing is you probably, if you look at it from the top, you should see a little notch on one side, or you should see a little dot. The first one to the left would be pin 1. And then what you do is you come around and come back up the other side. And this is looking at it from the top, right? You'll see the little notch, and you'll see the little notch in the top.
What?
No, this is the notch right there. That's the notch right there.
Oh, that.
Not the little. That's the injection molding. It's usually well defined. What, Jackson? You see it? Yeah. Might be a little circle. These packages were injection molded, and where the injection molding thing comes in, usually sometimes leave a little circle. But what we're looking for a sure enough notch. And when you're looking at the top, first pin on the left-hand side is pin 1. You number them down, and then do what? Come over and then number them up. This is a 14-pin deal. Y'all understand how I got that name? This is a standard package. What is this? Well, it could be a lot of different types of logic gates that would fit in a 14-pin package. In fact, it's probably more than one. Everybody understand that?
Top left.
A pin, yeah.
Top left, start with that first one.
That's the one. That would be pin number one. They're not, the pins are not going to be numbered because they figure you know how to number them, right? But you don't go down and then go over and go down. It goes down, then comes around and numbers back up, no matter what size they are. The biggest package that they ever came out with was a 64-pin package, which was 32 pins down one side and 32 pins down the other. Numbers the same way. Find the notch, look at it from the top. We okay?
So which one would be the top?
This is what I'm referring to as the top because that's the way I have mine drawn. It's the notch side.
Okay.
Okay, you okay? It could be your left, could be your right, depending on how you do it. Normally we like to hold it up like that because it makes it real easy to know where pin 1 is, right? Because you put it with the notch down, so we view them that way. So we can see all of these. So these are some 24-pin packs, I think. No, these are 18 pins, I think, because 24-pin went to I'd say my projector's not working. So I can't tell you. But these are different, all different sizes. We'll look at some different packages that's available. Now, we're dealing with what we call a hex inverter. What does hex stand for? It's hex. The decimal. Hex is 6. So a 7404 is a hex inverter. It means there's 6 inverter circuits inside that package. Okay. Now, if I was to look at the circuit, so this is the actual circuit that one inverter would be made out of. Yeah. That's one inverter. That would be plus 5 volts. That would be the circuit. But what you got to understand, and we'll look at a little bit about how this works, but it's not really important understanding how the circuit works. This is the symbol for an inverter. This represents that circuit. This says if I put a 1 in, I'm going to get a 0 out. If I put a 0 in, I'm supposed to get a 1 out. I don't care what the circuit is because I can't go in there and replace this. If this transistor goes bad, I have to replace the what? The whole thing. I have to replace all 6 of them. I can't replace one of them because they're all inside one package. So when you hold that thing in your hand, you got 6 of these. Now what we can do is we can share the common, we can share the plus and minus with every circuit inside there. So over here I could have another inverter. I'm just going to draw the circuit. So what we'll find out on these, we only need, on this guy, we need 2 power pins, right? You understand? So we got a power, we need a power and a common pin, right? You understand that? And then we need, how many pins? So we need 12 pins for the ICs because we got to have 1 pin dedicated to the input. We got to have 1 dedicated to the output. Right? You understand that? So I've got 6 of them in there. There's 12 pins, 1 for power, 1 for ground. So that's why we could only get 6 of them in a 14-pin deal. This makes sense. Now what we have is we have a drawing. So that's your dip, right? We have a drawing that we call this the pinout. Now what a pinout does is it shows us what's assigned to the pins. Now what they do here is they don't draw the circuit, they draw the symbol for the circuit, right? You understand? So if I wanted to make this thing work, I would have to take this. By the way, in TTL, VCC is equal to 5 volts. And of course, this is going to be common. I hate that they call it ground. So there's my power source. So before this thing works, I would have to take plus 5 volts and connect it to what? To pin 14. I would have to take my common and connect it to pin 7. As soon as I do that, I've powered up all 6 circuits inside the IC. If I wanted to hook up to this guy, then I would bring this signal in on pin 1, and I would hook up whatever I'm running with this inverter over to pin 2. It has nothing to do with the one next to it. It's just a different circuit inside the same package.
I understand it, though.
Yeah.
That drawing you did earlier.
Well, you don't need to. We're just going to learn some characteristics. We're going to have to learn, okay, how much current is required for a high on input? How much current is required for a low? Because we're going to have something called fan out, because this output cannot drive an infinite number of other circuits. It can only drive so much, right? So we're going to have to know the characteristics. How much current can that output drive? Right? You understand? Because that'll tell me what we can drive with it, right? How much does an input? If I input into that input, it's going to require current. That high is going to require current. How much does it require? We call it fan out. How many light devices can an output drive? So we'll look at that. So the data sheet's not going to show you the circuit, right? You understand? It's not going to show you that it requires all those transistors, that it required what? 1, 2, 3, 4 transistors just to get an inverter. But notice, this is my input. This is my output. I'm inputting on a transistor. I'm outputting on a transistor. So this is TTL. This is why this is called TTL. I don't need to know what the circuit looks like. All I know is my inputs are on a transistor and my outputs are on a transistor. That's what TTL stands for. I don't need to know the circuit. So what if this guy right here goes bad? I got to replace all 6 of them. I replaced the whole IC, right? You understand? It's not going to hurt to replace those other ones. Or if I got a spare one and I'm smart enough, I might move. A lot of times they don't need all 6. What if I only needed 1? I still get 6. So a lot of things, when you look at the data sheets, we'll look at some where it says unused gates. So that means if I was an engineer and I needed to add something, I could look at those unused gates that's inside these guys, and I might be able to do it without adding another circuit, right?
So I think you could leave it like it was on the same, like.
What you mean move it?
Like you said, where you still have to get all 6, you only have to use the one. Or you still go like just leave. Like you said, when one go out, and then you still have to replace all 6.
If all 6 were being used. If you had one of the gates in there that was not being used, you might be able to move over to the one that's not being used. That makes sense? Because if I'm going to use this IC, if I need 3, then I get 6, right? You understand? Because you can't split these circuits up. So a 7404 is going to be, we call it a hex inverter. Now, how did it get that name? Because there's 6 of them in there. We call the package a 14-pin deal. I can get AND gates in here. I can get OR gates. I can get NAND gates. I can get NOR gates. But this guy right here is an inverter. And to get the input, to allow the inputs to vary and get outputs varied, it takes a pretty good little circuit. But like I said, you don't need to understand how the circuit operates. All you need to know is, well, you do know what it operates. What does this say? It says if I put a 1 in, I better get a what out? 0 out. Or if I put a 0 in, I better get a what? I better get a 1 out. So if I put a 0 in if I put a 1 in and I get a 1 out, then something's wrong, right? You understand that? And then we'll figure out if it's this gate or if it's something downstream, and we'll show you how to do that. So if the output stays 0 all the time, then it might not be the gate. It might be somebody downstream that shorted out, right? You understand? We'll show you how to do it. So we can make an AND gate. Of course, if I put NAND gates, a 2-input AND gate, a 2-input AND gate would require how many pins?
You said 2 pins?
3 pins. Because you got to have an output. And people don't understand that. So every gate, when we say a 2-input AND gate, that's going to identify the number of pins that's on the input. But we've always got to have a what? An output.
And that's for the AND.
An AND gate. This is the symbol. This is the symbol of an AND gate. And this would be a 2-input AND gate. Now this would be a symbol for an OR gate that represents the circuit. So I could come in here and I could come up here and I can draw that entire circuit, right? Because that's what's actually in there. But what we do is we have symbols that represent logic functions. So this is a symbol for a what? And this is a symbol for a OR. Now, how do we do? How's the circuits for an AND? How's the circuits for an OR? I don't care. All I know, it takes all highs to get a high. So if I came over here and put this and this, then I would expect that on the output. Right? You understand? Because it takes all highs, all the whole expression is all the inputs have to be high to get the output to go high. That's the expression. That's an AND. But so if all highs, it takes all highs to get a high. If you don't have all highs, then the output's going to be what? It's going to be low. By the way, I should explain that too. So we use this a lot. High and low. We use that in addition. So a high is going to represent a voltage, right? And then a low is going to be 0 volts. Now TTL runs off a 5-volt supply, so the outputs will never be 5 volts because you'll save the circuit. We'll show you what's a legal high and what's a legal low and stuff like that. All I need to know is what's considered to be a legal low. What voltage should I measure for a legal low, and what voltage should I measure for a legal high? Normally, it'll never be what you power up off of. So if I power on 5 volts, my high will never make it to exactly 5 volts. So what's going to be legal, we need to know the range. And if I know the range, so if I come over here and it's low and it's sitting at 1 volt and it's supposed to be 0 volts, I know I've got a problem, right? You understand? But how high can it go? And still be considered, still work with all the neighbors downstream. Well, see, that's one thing we're going to look at. And where would that information be at? It's going to be in the data sheets. So the data sheets are going to show us what we consider to be illegal highs and what we consider to be legal lows. And of course, in truth tables, for a high, we're going to use a what? A 1, and for lows, we're going to use 0. So we'll use highs. So now that makes sense now, right? All inputs for an AND gate, all inputs have to be high to get a high on the output. Well, what do I say here? Well, here I'm going to say any, right? If any input is high, give you a high output. Now we're going to shorten this down. What I say is for ANDs, I start off with my inputs. I say all highs equal a high. That makes sense? On my OR gates, I'll say any low gives me a low. I'm sorry, what did I say? Any high gives me a high. I'm thinking of another gate. Thank you. And this is a problem we have, you know. So what do? We come over here. About is the maximum number of inputs we can put on this symbol is about 4. But with 4 inputs, that would be 16 entries in a truth table. If I go above 4, what they do is they just extend the back here. They don't try to clam them in there. They try to keep the input set up. So an AND gate would be drawn like this. So if I was to do a truth table, this is an 8 input AND gate, that would be 256 entries in the truth table. But it still is all highs to get a high. So if I came over here and I saw this, the output would be low because that's not all highs to get a high. And that's why learning the expressions are better than learning truth tables. We have a way of reduction called Kurnoff maps, which deals with truth tables. But it works okay up to 4 inputs, but the more inputs you get, the truth tables become unmanageable, right? You understand? So we're not going to use truth tables. We'll do truth tables, but we'll do truth tables on these guys. Because if you can understand a truth table for a 2 input AND gate, then you can understand the truth table for what it would look like for an 8 input gate, right? You understand? Now what we do on an OR gate is we just add more wings like this for larger inputs. So they just add little wings like that. But notice on an AND gate, this guy right here should be what? Straight. And on an OR gate is supposed to be what? Curved. And that's the symbol for an OR gate, an AND gate. And what's the symbol for an inverter? So an inverter, we say a high in gives us a low out. So everybody okay so far? Any questions? So those circuits are nice. You know, like I said, I could draw the input of an OR gate. I'm going to show y'all on the next slide. We'll show y'all the actual circuit, the TTL circuit, that you're going to say, okay. Because you got to understand, we don't troubleshoot this from a component view. Well, the IC itself is a component. We troubleshoot it on understanding what I expect on the output, depending on what? Input. If my output does not respond to my input, I might have to troubleshoot a little more, right? Y'all understand that? Anyway. Okay, so we'll show y'all different packages next time, and then we'll get into some more ICs, and we'll look at the other 3 basic. We have 5 basic gates, guys. All logic consists of 5 basic gates, no matter how complicated it is. Huh? Well, bring it up here and let me show you. I need these back. I need to bring them back up to me.
7, 14, and power, right? And then you say.
Well, on this guy's 7 and 14.
On this one.
So there's a notch. There's pin 1. There's pin 14. So my power would be between this pin and this pin.
And that's always. If I'm using that, I have to have power.
If you're using a 7404.
Using that one.
Well, no, if you're using a 7404 in a 14-pin pack, pin 14 will always be power and pin 7 will always be ground. But you can't say.
But no matter which one I'm using, there's always a power and ground. That's my question that needs to be connected. It's
oh yeah.
Like 1 and 2, like that's not.
Okay, so go out to your car and disconnect your battery.
I mean, I know it's gonna happen then, but.
So electronic devices does not work without a power source. So all integrated circuits are there power pins on this guy right here. Yes or no?
Yes.
You don't even have to think about it. It's an electronic device. It's got to be what? Powered.
Right.
Yeah.
Okay.
Yeah, and it's DC too. Is there power? So every one of these ICs, some of the pins are dedicated to power, right? And some of them's dedicated. So one of them's going to be a plus DC, and the other one's going to be your common, right? You understand that?
So your common is going to be 1, and your voltage is going to be your last one.
No. It's one of the pins, at least one of the pins is going to be the power pin, and one of the pins are going to be the common pin. Don't get your mind. In fact, these guys, the pins are.
Which one? Okay.
Normally it's 14 and 7, or it's 18 and 1. I mean, it's 18 and 9, or it's in the center, like 3 and 3 and. So that's one thing you don't take for granted that all these guys don't take for granted that this is the power pin and that's the ground pin. Technically, it could be the pin, but most of the time they either use those pins or they use two in the middle, two in the sides over here.
But
So that's what I would do if I.
They most don't always start. You count your normal pin where your
Yeah.
arch at the top.
Yeah.
That's gonna
So
be
look at
one.
this guy right here. This is pin 1. I go down, I come over and come up. Now, which one's power, which one's ground? I don't know. I just know they're there. But I'd look up the part number on the data sheet, and that would tell me if it's not a custom chip. So on microprocessors, they use multiple power pins and they use multiple grounds because those suckers use a lot of power. So instead of having one big old pin that handles 100 watts of power, they'll share it a bit on several pins. So you ever looked at the pin out of a microprocessor, you'll see VCC all over it, and you'll see common pins all over it too. Where's my ICs at? I got 2. The ICs, y'all. Oh, here they are. I got them. Got integrated circuits. These are ICs. They were right here. And I dropped. Those are welding. Yeah, it has 3D goggles and stuff, and you act like you're welding.